Hi, this is the continuation of the last topic regarding the convergence and divergence series. So according to this ratio test, we found the limit of this ratio test equal to L. We previously proved this series of convergence when you have the L strictly inferior than 1. In today's video, I'm going to prove this series is a divergent series when you have L strictly superior than 1. As we know, the third case, when you have L equal to 1 as a ratio test, doesn't provide any information, okay? In the other word, we have to use the different tests in order to know the series whether converges or diverges, okay? So let's move on to the proof now. So now I'm going to prove this series diverges when you have L strictly superior than 1, okay? I'm going to use the limit definition that exists R such that L strictly superior than R strictly superior than 1, okay? Let's set epsilon equal to L minus R, okay? So we have L greater than R greater than 1, okay? So there is some capital N such that N superior or equal to capital N according to the limit definition. So absolute value of A sub n plus 1 over A sub n minus L strictly inferior than epsilon, okay? The epsilon is a super small arbitrary, so this is equivalent to minus epsilon strictly. I'm going to work on the left hand side of this inequality. I will have minus epsilon strictly inferior than absolute value of A sub n plus 1 over A sub n minus L, okay? Strictly inferior than epsilon, okay? So I'm going to work on the left hand side of this inequality. So this one implies I'm going to bring this out to this side. I will have L minus epsilon equal to R, okay, equal to R, because if I'm bringing this R to this side, I will have L minus epsilon, I will have R strictly inferior than this absolute value of A sub n plus 1 over absolute value of A sub n for all superior n superior or equal to capital N, okay? So we'll have absolute value of E is capital N plus 1 strictly superior than R, so multiplied by absolute value of A sub capital N. I'm going to move on to the second term of this sequence. I will have E sub n plus 2 strictly superior than R is multiplied by absolute value of A sub capital N plus 1, which is greater than R squared, is multiplied by A sub capital N. I'm moving on to the third term, A sub capital N plus 3 strictly superior than R is multiplied by absolute value of A sub capital N plus 2. So this one is greater than R cubed, is multiplied by absolute value of A sub capital N, okay? I'm going to collect all the terms on the left hand side of this inequality and all the terms on the right hand side of this inequality to see what's the expression. By adding all these terms, I will have the sum of A sub n absolute value as n goes from capital N plus 1 to infinity strictly superior than, by adding all these terms, I will have R plus R squared plus R cubed and all the way down. The whole thing is multiplied by absolute value of A sub capital N, okay? So this one, what is this? This one geometry series. So I will have is strictly superior than the sum of this series R to the n, as n goes from 1 to infinity, is multiplied by absolute value of A sub capital N. So this one as we know, we have R superior, strictly superior than 1. As we know, this is the geometry series, but is divergent series because we have R strictly superior than 1. Okay, so this is divergent series. By using the comparison test, we conclude this series on the right hand side of this inequality is divergent as well, because this one is greater than this one. So this series as a whole series, which is a sub n as n goes from 1 to infinity, of course we have absolute value here, equal to this sum of absolute value of a sub n as n goes from 1 to the capital N plus another sum of absolute value of e sub n as n goes from capital N plus 1 to infinity. Okay, so we have these partial sums. This sum as a whole sum equal to this sum as n goes from 1 to the capital N of absolute value of e sub n plus another sum which is from capital N plus 1 to infinity of absolute value of e sub n. We prove this sum is a convergence by comparison test. So we found this sum, this partial sum, as a divergent sum because of comparison test. This is the whole sum is arithmetically going to be divergent as well. This one is implies. So thus this series is e sub n as n goes from 1 to infinity is a divergent series when we have R strictly superior than 1. Okay, let's move on to an example to support this one. Okay, let's move on to an example as a support of this proof. So I'm going to calculate the ratio test of this one. So you have the limit of e sub n plus 1 to the n plus 1 over n plus 1 factorial over n to the n over n factorial as n goes to infinity. This one equal to n plus 1, okay, to the n plus 1 over n plus 1 factorial is multiplied by n factorial over n to the n. Let's call this limit L. I'm going to simplify this one. So we'll have n plus 1 is multiplied by n plus 1 to the n, okay, over this factorial n plus 1. I can rewrite n as an n plus 1 is multiplied by n factorial, is multiplied by n factorial over n to the n. I'm going to simplify n factorial with n factorial, n plus 1 with n plus 1. I will be left with n plus 1 over n to the n. I'm going to simplify this one. I will have 1 plus 1 over n to the n. Okay, I'm going to apply natural log on both sides. I will have natural log of r equal to n is multiplied by natural log of 1 plus 1 over n. I'm going to apply the limit on both sides. The limit as n goes to infinity. The limit as n goes to infinity. So this one, I can replace 1 over n by t. So I will have natural log of 1 plus t. The limit as t, we have n goes to infinity. So if you replace t equal to 1 over n goes to infinity, that means t is going to 0. Okay? So this one minus natural log of 1, because natural log of 1 equal to 0. So over t plus 1 minus 1. Okay? This one is equivalent to the derivative function of this function, natural log of, so equal to derivative function of natural log at the points 1. Okay, so if you derivate natural log of x is given as 1 over x. Okay, so natural log of derivative function of this natural log equal to 1. So this one equal to 1. Okay, so since we have natural log of, since you have the limit as n goes to infinity, limit to natural log of L equal to 1, this implies L equal to E. Okay, so L equal to E strictly superior than 1. That's mean this series is finally this series A sub n as n goes from 1 to infinity diverges series. Okay, so I have done with this problem. Just consider subscribe. I will see you in next video. Bye.